Everyone, my name is Thomas Tuzel. I'm with Assured Information Security, aka AIS. We're a company out of New York, but I'm from an office in Colorado, which is just a small satellite office that sits out there. The company is interested in a lot of things, particularly hypervisors. Our office in Colorado particularly likes when Intel releases new features, so we kind of get excited whenever we see that sort of thing. And I'm talking about hypervisor introspection from the position of an unprivileged guest. So basically, think about a Google Cloud or AWS instance or something like that. We were interested in, can we detect whether or not a provider like that is introspecting on you and detecting or introspecting and getting information from you inappropriately. So a lot of organizations are moving to the cloud, right? It's easier for a lot of different reasons: scalability, manageability. You don't need to have as many IT staff on hand anymore, so it'll save you a decent amount of money. But the consequence is that it's not your hardware. It's not your system anymore, right? You can launch a guest, but that's usually the limits of what you can see and what you can do. So a hypervisor is sort of the big cheese in this situation, right? It can do a lot of different things, whatever it wants, right, without really leaving behind much evidence that it did something. So think about, if your operating system on your laptop had an evil kernel on it, right? There's not a whole lot you could do if it was properly designed to be evil. It's the same situation here. So you have an interesting paradox. Your organizations want to save money. They want to make things easier for them, but they have data they don't want compromised, right? They don't want to go through that whole process, which is going to cost them astronomical amount of money. So this is not anything that's really been that's new, right? This has been something that's been going on for a while, but most of the work that's been done for this focuses on whether or not something's already happened, right? They usually look for artifacting, right? So say hardware or software artifacts, something's been left behind, and that can vary from hypervisor to hypervisor, even version to version of the specific hypervisor. So we wanted to see if we can detect this happening as it happens, right? So with that being said, the hypervisor's behavior is not exactly invisible, right? It's trying to provide a real environment to your guest, but you're not really running on the hardware, so it does its best to do it, but there's evidence that it's there, right? Like it'll modify execution times because it's trying to do things in the back end. It'll modify the caches and that sort of thing. So we can use that to our advantage, right? So we set out to implement two different things to prove out whether or not we can detect that something's going on. So the first thing we did was we built a test framework, which is basically just an evil hypervisor, and then that would do introspection on our benign guest. And we wrote a module which has a variety of different sensors. Now, this module was designed to have very few dependencies, just be able to run pretty simply on a standard Linux box. So for the test framework, we used the Zen project, so usually just called Zen. It's an open source hypervisor. It's pretty popular. I'm sure most people have heard about it. And we added some capabilities to support a hypercall so we could turn on and off introspection capabilities. So hypercall is basically what a system calls to the kernel. The hypercall is to a hypervisor. So we just want to be able to call down to the hypervisor and tell it to do different things. We also added in some instructions for supporting what's called VM exiting, which I'll talk about in a little bit. So we also wrote a module with sensors, as I mentioned before, which had several different sensors in it. So the first one is an instruction intercession sensor. So it would basically detect whether or not the instructions are being dorked with by using a timing mechanism. We also have an active memory intercession sensor. So basically we wanted to see if we can detect whether or not a hypervisor is sitting and monitoring a memory access, and can we detect whether or not something's happening live. So that means that the hypervisor is sitting and waiting for you to access a portion of memory, and then it jumps in when you access a portion of memory and does its thing and returns back. We also wanted to see if we can determine whether or not passive memory introspection is happening, so we wrote a monitor for that. That basically means that we're mapping in memory from outside of the guest itself, right? So we don't want to directly interfere with the guest's operation when it's accessing memory. We want to be able to access that memory externally through some other mechanism. And finally, we looked into non-temporal access sensors, which is a mouthful, but basically non-temporal means it doesn't cache, right? It doesn't touch the cache. So that will become important later when I talk a little bit about some of the cache attacks that we're using, but it just adds a layer of difficulty to some of these detection techniques. So I want to jump in a little bit of background. A hypervisor is typically broken down into two different types. You have a type 1 and a type 2 hypervisor. The type 1 hypervisor sits directly on the hardware, right? You boot your system up, and you're in the hypervisor. Well, more accurately, you're in the privileged domain of the hypervisor, where you can control the hypervisor if you need to. The second type of hypervisor is a type 2 hypervisor, which sits on a host OS. So if you think about, you have a Windows box and you install VirtualBox on there, and then you launch a guest instance from VirtualBox. That would be a type 2 hypervisor. So we're going to be using a type 1 hypervisor, and that's what Zen is. So a virtual machine exit, which I promised I'd talk about later, is an operation that happens quite frequently on a VMM, aka hypervisor. So a hypervisor needs to monitor and modify things as needed. So whenever it needs to retain control and do something for itself or distribute the load to somewhere else, it needs to pause the existing guest. So when it does that, it'll store everything in what's called a VMCS, a virtual machine control structure, which resides in memory and exists for each different virtual CPU that exists on the guest instance. So it'll save everything off and then return control to itself via VM exit, do whatever it needs to do, and then return back via VM entry to the guest again. This kind of thing incurs a pretty substantial overhead because it's a very large world switch, or I should say very expensive world switch, so we can use that to our advantage. We're going to be using a few different types of timing mechanisms. The first one is called the timestamp counter, usually just called the TSC. That is a cycle time resolution counter that starts up whenever the system starts up and just counts the number of cycles since the system has started. The hyper-precision event timer is what used to be called a multimedia timer, but basically it's used for any kind of audio, video, graphics, or whatever else you have on your operating system. It runs at a much lower resolution. It can be around 10 megahertz or something like that. But I'll talk about why we're going to use that a bit more later. Finally, we're going to supplement all of this with thread racing techniques, so we can basically use two different threads and correlate them to determine whether or not how long something takes to run based on the amount of operations that a certain thread has done. So I want to emphasize this early on. When we're trying to time memory operations, your typical operating system is going to use hardware accelerated paging, right? It's pretty fast. But when a virtual machine introspection is happening, the hypervisor has to rely on usually software acceleration, right? It can't use hardware for some of the things it's doing. Thus, it's going to be a bit slow. Another thing we're going to be leveraging is what's called libVMI. It's a virtual machine introspection library that was written by someone who now works for us, although he did the work outside of the company. It's available on GitHub. It's open source. You can either go to libvmi.com or just Google it. I'm sure it'll come up with the first hit. But basically, it makes virtual machine introspection pretty easy. You can do modifying of page permissions. You can read and write memory. You can map in memory. A lot of different things. You can even have it open up tabs for you on someone's browser. It just makes life easy, and we're going to be using it for some of our virtual machine introspection work. So a little bit of background on caches in the CPU. I'm not really going to dive into this too much. I just wanted to give a quick background on what your basic cache looks like. So the important thing is that you usually have 3 levels of cache on your CPU. And now in this case, I have a 4-core CPU. And L1 and L2 caches will sit on each core. The L3 cache is shared amongst all the cores, and that's what's really important for some of the work we're doing. We don't need to worry about an operation happening on any specific core. We just need it to happen on the CPU in and of itself. So this is your basic cache, right? Most caches are going to be set associative. This is a very compressed version of what a cache might look like. But let's say you have 4 sets and 4 ways. So each set has 4 ways. Plus you have 4 cache lines to each set. So later on, when I start talking about flushing a cache line or something, this is kind of the structure I'm looking at, talking about. Now, there's a lot of different cache side channel attacks that take advantage of the cache hierarchy. This is a sampling of all the different types of cache attacks that are pretty common. You don't need to remember all these, and I'm not going to go over all of them. There's 2 here in particular that are of interest to us, which I'll get into in depth later. But these all work in many different ways, including just targeting a shared virtual address or going after using eviction sets. So an eviction set is basically a set of virtual addresses that will correspond to cache lines in the cache itself that you can use to determine whether or not some operation's happening or not. Right. All this usually relies on a timing mechanism. So loading up something in the cache line, in the cache line, and then seeing if it's still there by trying to reload it or by trying to prime it again or something like that. Again, I don't want to go over all this right now, and I'm not going to get into super huge depth with all this, except for the stuff I need to later on. Right, so now let's talk about each one of the different sensors. So Again, a hypervisor will modify guest behavior based on a number of different reasons, right? It might need to just determine what kind of information is on the guest for some reason. It may just need to modify the guest's behavior for load balancing. Maybe it just needs to know when it's going to do something, just so it can do, general load balancing or not, or any kind of any other number of things it might want to do. But we can use the timing to determine, whether or not the hypervisor is trapping, how much work it's doing, that sort of thing. So we're going to be drawing some baselines from some other instructions to determine, what timing is suspicious, what timing is not. So some instructions will trap unconditionally, right? They'll trap every single time you run them in hardware. So an instruction like CPU ID, which you can probably guess is returning identification information for your CPU. So think about your guest that you launched in a hypervisor. It's not literally going to have access to your specific CPU that's running in the hardware. It's going to be seeing what it thinks is the hardware that it has. So each time it runs CPU ID, the hypervisor needs to jump in and say, this is what you actually have available to you as far as your resources go. So it's going to have to trap every single time. Now, an operation like move to CR3, which is manipulating the base of the paging hierarchy, doesn't always need to trap, right? So that was one we can't really rely on as much. So when we do timing for this, we're going to use wall timing with the HPET. So I talked about the HPET before as the multimedia timer. The reason this is reliable is because the HPET is used for multimedia. So if it was being manipulated by the hypervisor, then things like your audio or your video or your OS graphics or something like that would be skipping around, and it was pretty obvious something's going wrong. So we can use that as our base timing source for wall timing. So we can also use thread racing, so basically running two threads, and we can pin them to a different core if we'd like, and have one of them run NOPs because NOPs are really fast, and then basically count the amount of NOPs that run while our main thread of interest is running. And we can use these two things to supplement each other, right? So if one of them shows weird timing, the other one doesn't, then we may know that something may not be quite right, but we can use them to supplement each other to be really sure that something's going wrong. So active memory intercession, again, is the hypervisor introspecting directly on a memory operation again. So remember, the guest is accessing memory, the hypervisor interferes and does its thing and then returns back control to the guest. So this can happen with an EPT violation. So the extended page tables basically allows virtual to physical mappings for a guest. So we can mark the page as to have some different sort of permissions that cause a violation and then return back exit to a hypervisor, right? So that the guest is doing its thing, accesses the page throws a violation and returns back control to the hypervisor. The hypervisor has to do something, otherwise the system would hang. So we can use libvmi to do this, and it'll just mark the pages we need to, and then cause an exit. And we can do this for like read or write or whatever else it is we want to do. This incurs a pretty large overhead overall. So this is basically what this looks like from libvmi's perspective. So if you're sitting on a privileged domain, which is basically the domain you're controlling from. So again, remember when I mentioned that you boot the system up and it kicks you into a privileged domain. That would be what's usually called DOM0. Especially in the case of Zen, they call them domains instead of guests. DOM-U is just your unprivileged domain that your guest that we're trying to determine whether or not introspection is happening. So basically, from this point, DOM0 will grab the directory table base or the process ID from DOM-U, and then it'll either walk the OS process list or it'll get the physical address by walking the guest page table. So it does this from a whole bunch of different caches. libvmi has tons of caches and it automatically maintains them all. And then it'll call down to the hypervisor and say, update this page permission to cause an EPT violation. So again, when something's read or written to that page, it'll cause a violation. It'll return control to the hypervisor, and the hypervisor can do its thing. So it'll send that down, and the hypervisor will obtain the guest page frame number, and then translate it to the machine frame number, and map that memory back into DOM0. So again, this is all updated automatically by libvmi. It does all this stuff for you in the back end. So passive memory monitoring. So again, let's say the hypervisor wants to be more stealthy than just actively interceding every single time you access a portion of memory. So you can map in the guest physical pages without actually directly interfering with the guest memory operations. So you may be asking, well, yeah, aren't there a whole lot of other memory translations that are happening? Yeah, there are, but Intel's doing all this stuff for you in the hardware, so there's nothing to worry your pretty little head about. But this is basically how it's going to work. But we can use a timing operation to determine whether or not memory lines are being accessed in the hardware, right? So whenever you're accessing something in memory, it's usually going to end up in the cache. Not always, and I'll talk about that a bit more later, but usually it will. So we can use a cache attack. So remember I listed a whole bunch of different cache attacks. Well, this is one of them, and this is the one we use. And basically what happens is, in a flush reload cache attack, you can flush a memory line of interest, and it'll flush it completely out of the cache. And then we'll wait for some period of time and try to reload it. Now, if we try to reload it and it returns back really quickly, that means that something else is accessing that portion of memory because it's already there, right? It doesn't need to reload it twice. Whereas if we need to take more time to reload it, that means it's not there anymore. So a decrease in timing will be pretty indicative that something else is going on here. So this is basically what it looks like from libvmy's perspective from the privileged domain. It's going to do a lot of the same thing that I just mentioned before, right? It's going to either grab the DTB or it's going to grab the DTB or it's going to grab the PID, and then it's going to walk through the OS process list or get the physical address, and then it's going to ask the hypervisor instead to mmap in that information for it through the guest page frame number. And then the hypervisor is going to do that. It's going to look up the machine frame number and then return back that mapping to the privileged domain, and the privileged domain can introspect on the guest. So non-temporal access stuff. Basically, this is again the non-caching thing. So in some situations, there's a use for a non-caching instruction. A lot of times it's used for things like graphics, what have you. But non-temporal instructions are kind of interesting, right, in that we can't use the previous cache attack I talked about, right? It's not going to be in the cache. So there is a side effect of non-temporal instructions in that when you use a temporal instruction, for example, it's going to write it into the cache, right? But when a non-temporal instruction is used, it's going to check to make sure it's not in the cache, and if it is in the cache, it's going to flush it out. So we can probably use that to our advantage if we wanted to, and determine that that a non-temporal instruction is trying to be used to be sort of stealthy. Now that would require some other, error control and that kind of thing, right? The other thing is that Intel has a feature on their CPUs called PAT, page attribute tables, which can specify per page caching behavior to be non-cache interacting, right? So you can just say, like, don't cache this page. And then, now it won't be in cache anymore. So that would add another layer of complexity. So when we did this testing, we tested a whole bunch of different machines, including some cloud providers, and we derived some baselines for instruction intercession. So remember, I was talking about CBOD, for example, always trapping. So we basically use exiting and non-exiting instructions to determine how much out of whack certain things are. And we could flag things as being, either potentially exiting or of interest or something like that, depending on the number that we get. For memory intercession sensors, we looked at memory that was nearby, right? So something here and something there, and is this different than what's here? So when we did the instruction intercession, when we designed the evil hypervisor, we basically just had it trap and then return back right away to just prove out that the only thing you really need to do is a world switch to show that just the world switch all by itself is going to show that something's going on. So this is kind of what it looks like. This is the wall timing results, right? So using HPET. So these are all the different instructions that you generally are supported by hardware for trapping. Now, some of them can't exit, right? So you're going to see a non-exiting only case versus some of them have to exit every time, right? So remember CBOD right there always has to exit. Now, some of them, you can see a massive disparity between the two, like RDTSC and RDTSCP. Those instructions are used for reading the timestamp counter. Remember that really high resolution cycle time counter that I was talking about? Some of them, like the DR instructions, DR0 through DR7, are for debug registers. So those ones, you're seeing a pretty close correlation. The reason for that is that Zen will only trap on the first time it sees it and then leave it alone after that. So there's still a spike, but not as much of one. Now, in a real intercession scenario, I wouldn't be able to just trap once and really be all that evil, right? That'd be a pretty miserable attempt. But you can get the idea, right? It's a pretty large disparity between an exiting and a non-exiting case. Now, some of them we just didn't add in an exiting case because it'd be extraordinarily difficult for us to add it in, and the goal here wasn't really to write an evil hypervisor so much as just show that we can do this kind of thing. Here's the instruction timing. So remember the thread racing. These are just the results for the amount of NOPs we could run. So you can see there's a pretty similar spread for both of them as I'm switching back and forth between the two. So here's some other instructions for wall timing. Again, this is with the HPET. I put this on a separate slide because these ones are on a log scale. So they would just dwarf all the rest of the chart in the other one if I didn't separate them out. One thing to mention here is that the move nt dq a and the not a one are basically they're not actually being trapped exactly as the instruction itself. They're being trapped whenever they access memory. These are non-temporal instructions. I just put them here to kind of keep everything together. But again, you can see that this is the instruction timing case. The results are pretty similar between the two. So, right, I mean, it should be pretty apparent that a hypervisor that was benign wouldn't do this very often, because this would take a pretty substantial workload away, and only a really dedicated hypervisor would want to do that. So this is the active memory intercession. We're just showing different pages, and you can probably tell which one is the one that's being trapped in this case. Again, this is log scale, so obviously the fourth offset is getting trapped, and it's incurring a pretty substantial overhead overall. Right, so again, a hypervisor probably wouldn't want to do this very often. Now, passive mappings are, again, mapping in from outside the guest, right? So this is a more stealthy way to do things. And this is measuring for specific cache lines. So we can measure down to a resolution of 64 bytes, which is the length of the cache line itself. So in this case, we're introspecting on memory at offset 80. So that one is, showing the lowest timing. Now, there's the two memory areas adjacent to it are a bit lower, and the reason for that is that the prefetcher is predicting that we're going to be accessing that memory. In this case, it was wrong, but Intel is trying to help us out. But you can kind of see the sinkhole design that's supposed to happen. Right. So again, you can see that these kind of operations will definitely affect the cache, and we can use that to our advantage. So there's a bunch of other work that could be done for this. This was sort of our initial look to see how much we can get away with when we do this. We would look to do like a continuous detection environment to actually detect memory areas of interest that are of high value. More robust classification could be used, that sort of thing, as well as a response strategy to say like, well, when you're being introspected on, do you smash everything and run away, or do you play along and not give away that you know that something's going on? Now, I want to jump into a bit of background on things that can make this easier and or harder for detection mechanisms. So these are the different guest modes that you can use when you launch a guest, right? So we were using the hardware HBM guest when we were running this. So there's a whole bunch of different ways to do this, though, right? So you can run a para-virtualized guest, aka PV guest, which doesn't have any kind of hardware support. So when we do this, we use VTX, right, the virtualization extension. But you can run this straight in the software. Now, the benefit of doing that in the software is that it's usually cheaper, like fewer dollars to do this, but the performance won't be as good. And also, the address space is shared across the hypervisor and the guests, which is not really the greatest security, personally, if you ask me. So we use HBM. HBM supports virtualization extensions, so we can do a lot of the operations that we were talking about. However, HBM uses QEMU emulation for device interfacing, right? So when you think about accessing your NIC, for example, it's going to be using QEMU. The consequence of using that is probably performance, but also that any kind of vulnerability that QEMU may suffer from, you'll probably be suffering from too. I don't really know how secure, how good QEMU's codebase is. I never looked it up on ExploitDB. But, it's just something to consider. PVH is kind of a shiny new guest mode. That's a sort of a combination of different guest modes, but basically it's using BTD, which I'll talk about in the next slide. And it avoids, and thus avoiding the use of QEMU. So, it should offer some performance improvements, security improvements, that kind of thing. Now, VTD is basically allowing the devices to interface directly with your main memory. So, in your typical CPU, you have an MMU, right, a memory management unit that does the virtual to physical translations for you for operations that run through the CPU. Devices have kind of the same thing, right? They have device addresses, and they need to be able to store things in main memory sometimes. So they use IO MMU to do that. Thus, they can store things in main memory. Now, this kind of opens up an interesting door. If you have a rogue device that interfaces with your main memory, whether it's rogue because it's just poorly designed, it's maliciously designed, or because it just has bad drivers or whatever else the reason is, could it manipulate your memory and cause exploitation of your system? I'm not saying this has been happening, but it would make a fantastic conference talk if someone could find something out about that. But it's just something to keep on the radar. Some other technologies that are out now include virtualization exceptions. So when we manipulate memory, we're using a VM exit, right? It's a full world switch. But there's another way to do this, including using virtualization exceptions. Which, if you think about, like, let's say you look on the Python try except block, you basically have your code running, and then if something goes wrong, there's an exception. If there was an exception, you jump to and you handle whatever is in the exception. So it's the same kind of thing here, which basically means that it's a little bit, it's not as quiet, because the hypervisor needs to actually embed the virtualization exceptions into the guest, right? So the guest needs to be able to see it. So if you're going to do something like this, you have about 10x less overhead, but the guest will have to be aware of it. Whether or not the guest is actually checking for it is a different story. So it just depends on, you know, how good you are at gauging your guest. So one of the other cache attacks that I said I would talk about is the prime abort, and there's also a more naive TSX-based technique. So this uses a hardware callback instead of using a timer. So when I talked about flush reload before, flush reload relies on timers, right? So there's a lot of possibility for noise to enter the system from other guests or for whatever else. TSX is a technique for transactional memory. So TSX enables the capability to use transactional memory on the processor. It basically allows multiple threads to be running without actually needing to be serialized. So usually you had the whole thing with critical regions that would only run one thread at a time until it got out of the critical region. But this basically allows you to run your multiple threads, and it'll only cause an abort or prevent a write back if it detects a conflict. So prime abort was an attack that was found last year and presented at Usenix, and basically it just allows a hardware callback instead, right? So you can mark memory and just wait for like the memory to be accessed, and then it'll just cause a hardware callback. So it opens up a lot of doors in terms of robustness. It reduces noise issues and that kind of thing. Prime abort relies on eviction sets, whereas a more naive technique can use just shared memory. So you can basically just say, cause an abort whenever the shared memory is accessed. Another thing that's on the horizon from Intel is subpage permissions. So that basically allows you to do memory protection at a much lower granularity. So when we were marking pages to exit before, right? Remember when I was mentioning that a page can be marked to have different permissions to cause access violation, and then trap back to the guest. So Intel's been working on a way to do this at a lower granularity, right? So instead of having to manipulate the entire page, it'll just trap subpages, right? So your typical page is going to be 4,096 bytes, typically. But let's say you can do this at 128 byte granularity. So instead of checking every single 4,096 byte page, we have to check every 128 bytes of subpages, right? So there's a lot more area for us to cover. Specifically, 32 times in this case. Now this is still being worked on. It's not fully supported right now. Last time I checked. Another technology is the Intel cache allocation technology. So Intel has released this for generally very high-end CPUs. So like your laptop's not going to have this. This exists on some of the really ritzy Xeons. But this allows process isolation on the last level cache. So last level cache meaning the L3. So you can basically say this process is going to be in protected cache space, and this process is going to be in another cache space. This would allow a lot of cache conflicts and side channel vulnerabilities by preventing access of different things to different parts of the cache. Again, your laptop's not going to have this on board, so and the other issue with this is that there's no proof to the guest that this is actually being enforced. The only real way that a guest could prove that this is being enforced is to attack itself. But then you have an interesting, issue of, well, you attacked yourself and the hypervisor was running this at the time you did that, but maybe now it turned it off. And you have no real way to prove this unless you keep doing it, and even then it's kind of not really clear that's going to work out. So this is an interesting technology. Maybe they'll modify this in a bit in the future, and then it'll be useful for this kind of stuff. So 5-level paging is also an up-and-coming thing. So, as time marches on, people need more space. Turns out that some people, some systems already are still already running out of memory, right? So This is a diagram of a 4-level paging setup, and basically the issue is that we have 256 TB of virtual address space, but that's not enough for those of us who need more memory than that, which I know is totally me. But so the 5-level paging increases that to 128 PB of virtual address space, and it increases the physical address space from 64 TB to 4 PB. They do this by inserting the new level called P4D in between the PGD and the page upper directory. Now, the consequence of doing something like this is that you have more address space now. So when you do an eviction set relies on finding an address that corresponds to an area in the cache. Right, so when you're building an eviction set, you need to build up a set of addresses that target the specific cache lines that you're interested in the cache set. Now, if you have more address space, you have more addresses to work with. So that increases the ability for you to build an eviction set, which is important for a variety of different cache attacks, including prime and probe. In the case of prime and board, it's also important. So the one technology that will help with introspection is Intel's SGX. So Intel SGX is a technology that will allow you to encapsulate your interesting data in an enclave. Right, so you can have your trusted components and your untrusted components sitting in SGX, and you have an attestable way to tell that that your data is being securely encapsulated in there. Now, this usually works except when someone finds a security vulnerability like Foreshadow. Foreshadow was using, it was able to tell based on prefetching behavior that to derive, what should be private information. Usually this works until someone finds a vulnerability, but this is the one thing that is attestable right now that helps with hypervisor introspection security. Now, one drawback for this for a lot of organizations was that there was no offline support for this. Right, you needed to have access to Intel servers to connect back to them. Now, as of August of this year, I think they just published this in the middle of August. They released the ECDESA attestation key for offline support for this. So there's a lot of customers out there that just don't connect their stuff to the cloud. I should say connect to the internet. So this solves that issue. So I want to run a demo really quick of how this works. And it's a video because I'm not going to do a live demo. I don't have the guts for it. Okay, so on the left is going to be your DOM0. That's going to be the privileged domain, and on the right we're going to have our unprivileged domain. So we're going to create our guest really quick, and then access it. So the first thing we're doing is just creating it from the configuration file that we have, and then kicking directly into the console. So you get to see Ubuntu boot up, which is very exciting. Don't worry about it. I can tell you the network manager started. Awesome, right? I mean, I guess I was hoping you could read it, but it looks like the predicted resolution is too low. Oh, I thought you meant like the actual size of the text. Oh, no, I can confirm that Ubuntu definitely booted. Yeah, trust me. I actually had to build this image myself because I couldn't find a Ubuntu image that directly boots into the terminal as a live image. I'm still kind of proud of myself. Not really. Okay, so we're going to clone the project into our unprivileged guest, which we just SSH'd into, by the way. Build it. Okay, so we're going to run the base instruction timing. So again, remember all the instructions I was showing you that we're testing to see how long they take to run. Okay, so there you go. Hopefully you can read that, but you can basically see the wall timing on the I guess it's kind of the left center column. That one shows the HPET timer, and the other one is showing the NOP timer. And so you can see also the we flag whether or not something's suspicious or not. RDC right there at 0, that's usually used for crypto, and it's showing 0 because the CPU that we're testing it on in this case is not supported, does not support RDC. So now we can toggle whether or not an instruction is going to exit or not using our hypercall tool on the privileged domain. So we're going to modify the domain number really quick. We need to get the domain number that Zen assigns so that we target the correct domain. So in that case, it's 5. All right, so let's change that. And then we're going to run it really quick to have the hypercall send. Let's run it again. And so now you can see that RDTSC and RDTSCP have substantially higher timings. Before, if you can't read that, we're around 900 to 1100 for the 2 on the wall timing, and about 600 to 680 and 688 for the NOP timing. So now you're at, what, 46,000, 47,000, and then 18,000, 18,000, so pretty substantial increase. So now we're going to turn on RDRAND instead, which is another crypto instruction. Now it'd be interesting to manipulate crypto because you can just nullify it if you trap this instruction. Now with that being said, you could just access memory and door clip someone's crypto that way, but you know, it's an interesting thought. So now you can see RDRAND jump. Before it was about 11,000 and 4,500 respectively. Now it's 45,000 something, 18,000 respectively. And the tool flagged it as suspicious. So the non-temporal instructions are the ones that are at the very bottom, the move in TDQA and move in TDQ. So we ran those, and you can see that they have a pretty low overhead when they access memory. So now we're going to use libvmine to trap on a page access. So that's our tool just allocated some virtual memory for us. And we're going to use that address on our privileged domain. Right, so now we're trapping on the page access, and you can see the massive spike in timing, right? So it went to, what is that, like 6 million something? Yeah, 6 million, and then 2 million and 1.5 million on the NOPs, and it got flagged as suspicious instead of being like 200, 300 something. So we're going to run the memory timing really quick. So this is the active intercession. Right, so we're using the TSC here to do our tick timing, so we can use the instruction timing tool that we used before to I'll just really quick to verify that the TSC is okay. Because the TSC can and will be manipulated pretty frequently by the hypervisor, so we can use the HPET to verify that the RDTSC instruction is fine, and we can use it to time memory accesses. So that's what's happening here. So we are allocating virtual memory again. Right, and then you can see a pretty gigantic spike on the first page offset, 85,000 instead of all the other ones being around 40. All right, so this is the passive mapping timing. So we're basically doing the same, allocating memory again, and these are the timing results that we get. All right, so around 300-ish. All right, so again, let's just allocate some memory, and then this time we'll run it with the mapping happening on the privileged domain. All right, so you can see the first offset is around 83, which is a lot lower than the other ones. Thus, it's a little suspicious. Again, you can see that the one nearby is a little bit lower too. That's just due to the prefetcher behavior. So now we'll go after a different offset, just for posterity. All right, so you can see around offset 80, the value is a bit lower. Now the one next to it is also similarly low, but like literally one tick lower. So that happens sometimes. It's just the behavior of the prefetcher. It's just how the thing goes. So if you really want to be sure, you need to run this multiple times and do some process isolation and that sort of thing. All right, one more time. All right, so 100 you can see is the lowest value in that case. All right, so the rest of it is not really terribly important. We have a way to output this stuff to a CSV if you have some reason you want to use a CSV. Whatever floats your boat. Yeah, very exciting, a CSV, right? Okay. And there's also a simple help menu in here. Okay. So, what happened to my buttons? There you go. Back. Cool. Okay, so again, we just want to show that this kind of thing is possible. We can detect instructions being trapped and manipulated, as well as active and passive memory. There's some other work for memory operations that would be helpful in this case, like isolating specific processes and controlling for the fact that active memory intercession would raise timings, but passive memory would lower timings. So there's a bit of deconfliction that needs to happen here. Some of the techniques I was talking about would make this a bit easier in the future. They would require a bit more work, but that's just there's always new things coming out in this field, so we're pretty excited about this kind of stuff. But that would make some of these things, including noise in like a passive memory situation, a bit easier to deal with. But again, we just want to show what the limitations of doing something like this are. So we've open sourced all this work. This is available on GitHub. These are the links. So the toolkit is here. And at the ECR toolkit URL, and the Evo hypervisor, for those that are so inclined, is under the ECR hypervisor URL. We also have a published white paper that's linked on the on each of these GitHub repos. So feel free to go ahead and read that if I was too incoherent or something like that. But other than that, I want to open up the floor for questions. Thank you. Thanks. Oh, yep. So you were asking how detectable is it that a client is trying to infiltrate us? Yep. So not really, because a lot of the techniques, I mean, it's difficult, right? Like if you're running say a instruction timing thing where you're running two different threads and one of them is just running NOPs, you can run whatever you want, right? But you're just running instructions. How are they going to know that that's what you're doing? right? Especially since some of those instructions don't have hardware support to trap in the first place. So there's not really a way for them to jump in and say like, oh, this person's like running like a bajillion nops, like they must be going after us. And even if they were, change them to not be nops, right? So it's hard for them to do something like that. For something like a cache attack, right? You're flushing your cache. There's not really a good way for them to detect it either. One of the advantages of a cache attack called the flush, which I had on one of the other slides, is that it's stealthy in the first place because all you're doing is flushing the cache. You're not even loading anything in the cache. So that makes it extraordinarily difficult to detect. So the other thing is, running an instruction timer like RDTSC or something, it just happens all the time. So there's not really a whole lot of evidence left behind that you're doing anything. I mean, I guess they could read the memory to see that you're running this toolkit, but then change the toolkit so it looks like something else, that kind of thing. It's a cat and mouse game. Any other questions? So can you be more specific when you say fuzzing it or correlating events? Which events? Okay, yeah, no problem. All right. Any other questions? Cool. Okay, thank you.